Hi everyone, and welcome to this session on DBT Core Concepts. DBT, which stands for Data Build Tool, is a transformative tool in the modern data stack that empowers data teams to build, test, and maintain robust data pipelines efficiently. It's especially powerful when working with data warehouses and transforming raw data into insights-ready datasets. In this session, we're going to dive into the core concepts that form the foundation of DBT. Understanding these concepts will help you design structured, scalable, and maintainable data models while ensuring data quality and consistency. Let's explore each concept in detail. Let's break this down step by step. 1. Models. These are SQL files that define transformations on your raw data. Each model represents a single transformation. Think of it as a step in your pipeline where raw data gets shaped into something more usable. 2. Sources. These are your definitions of raw data tables in your data warehouse. Sources act as the starting point for your transformations and allow you to track and document where your data originates. 3. Tests. Data quality is critical. Tests in DBT are assertions that validate whether your data meets expectations. They ensure your transformations don't introduce errors and that your data remains reliable. 4. Snapshots. Snapshots let you capture and store the state of your data at specific points in time. They're perfect for tracking historical changes, like when you want to see how a customer's profile has evolved over time. 5. Seeds. Sometimes you need static data in your pipeline, like reference tables or mapping datasets. Seeds are CSV files that you can load directly into your warehouse and integrate into your transformations. 6. Macros. Automation is key in any engineering process, and that's where macros shine. These are reusable SQL snippets that help you standardize repetitive tasks, enforce consistency, and streamline your workflows. 7. Documentation. Last but not least, DBT generates auto-documentation for your data models. This makes it easier for your team to understand the context and logic behind your transformations, promoting collaboration and reducing onboarding time. It's also worth mentioning that DBT encourages structuring your models into logical layers: staging, intermediate, and Marts. This helps maintain clarity in your workflows, ensuring raw data is first cleaned and standardized in staging, refined and aggregated in intermediate models, and finally optimized for business consumption in Marts. Now that we've covered the core concepts of DBT, let's take a closer look at how we structure our DBT models, starting with the staging layer. This is the foundational layer of your DBT pipeline and plays a crucial role in ensuring clean, consistent, and well-organized data for downstream transformations. Here's what happens in staging. Defining connections to the data source. Staging models define connections to your raw data using DBT's source function. For example, in the code snippet you see here, we're connecting to the Stripe data source and its payment table using source, Stripe, payment. Typecasting and column selection. In the staging layer, you perform operations like renaming columns, applying typecasts, and ensuring your data is clean and standardized. This sets a strong foundation for downstream transformations. Tables. Typically, staging models are stored as views, not tables. Views don't occupy storage space in your data warehouse, making this layer lightweight and efficient. Organizing models. To maintain a clear structure, transformations are organized into reusable data models. You can even group staging models into subdirectories based on their source data, creating a logical folder hierarchy. Naming conventions. DBT emphasizes consistent naming conventions. For staging models, you use a double in the file names to indicate the relationship between the source and the entity. Let's look at the example code on this slide. Here, we're staging payment data from Stripe. In the source CT, we pull raw data directly from the Stripe source table using the source function. In the renamed CTE, we clean and transform the data. Columns are renamed to follow consistent naming conventions, like changing ID to payment ID. Values are standardized using SQL logic, such as categorizing payment methods or deriving payment as a Boolean field based on the payment status. Typecasting ensures that numerical values like amount are transformed into a standardized format, such as converting cents into dollars. Dates and timestamps are formatted to match your warehouse's requirements. Finally, we use a select asterisk from renamed to output the transformed dataset. By following this structure, the staging layer ensures that your data is clean, organized, and ready for intermediate transformations. Building on the foundation established in the staging layer, the intermediate layer is where we start to create more business-specific transformations. This layer bridges the gap between clean, standardized staging data and the final output models used for analytics and reporting. Let's break down what happens in this intermediate layer. Subdirectories based on business groupings. Just as we structured the staging layer by source, the intermediate layer can be organized into subdirectories based on business groupings. For example, you might group transformations by business domains like payments, orders, or customers. This makes your pipeline modular and easier to navigate. Building on staging models, intermediate models typically depend on the clean, standardized data from staging models. For example, in the code snippet here, we reference the STG and Stripe payments model using the ref function to pull data into our intermediate transformation. To maintain clarity, intermediate models use a naming convention that indicates the entity and the type of transformation applied. For instance, the file and pivot orders SQL tells us that it's an intermediate model related to payments, and the transformation pivots data to an order level grain. Materialized ephemerally intermediate models are often materialized ephemerally. This means they exist only during query execution and are not stored in the warehouse, reducing storage costs and ensuring that transformations are as lightweight as possible. Let's examine the code snippet on this slide. The first CTE, payments, pulls data from the STG from payment staging model using ref string for payments. This ensures we're working with clean, consistent data as our starting point. The second CT, pivot and aggregate payments to order grain, performs a more complex transformation. It uses a list of payment methods, defined as a Jinja variable at the top, to dynamically pivot data. For each payment method, the code calculates the total amount for successful payments using a conditional case statement. A total sum of all successful payments is also calculated. The group by ensures the data is aggregated at the order ID grain. Final select the transformation concludes with a select from pivot and aggregate payments to order grain, outputting the aggregated, pivoted dataset. This result is now tailored for further use in the Mart layer or business-specific analyses. Now that we've covered the staging and intermediate layers, let's move on to the Marts layer. This is the final layer in your DBT pipeline, where data is transformed into business-ready models designed for end-user consumption. These models are what analysts and decision-makers rely on to generate insights and drive business decisions. Here's how we structure the Marts layer. The Marts layer is organized around business-specific domains like finance, marketing, sales, or operations. Each domain gets its own folder, and within each folder, you define models tailored to that specific business function. Unlike staging models, which are often materialized as views, Marts models are usually materialized as tables or incremental tables. This approach ensures the models are optimized for fast querying and can handle larger datasets efficiently. Models in the Marts layer are named according to business groups or entities. For example, in the folder structure shown here, we have a finance folder containing models like orders.sql and payments.sql, and a marketing folder with a model like customers.sql. The finance models YAML and marketing models YAML files document the respective models in these folders. Let's break down the example orders.sql code. We start by referencing the staging model STG Jaffle Shop orders using ref. This brings in clean and standardized data for orders. Next, we bring in aggregated payment data from the intermediate model int payments pivoted to orders. In the third CT, orders and order payments joined, we combine the orders and payments datasets. We join them on order ID. Using Coalesce, we handle any missing values in the payment data, setting them to 0 where applicable. We include both the total payment amount and specific fields like gift card amount. Final, select the result is a business-ready dataset at the order level, combining order details and payment information, which is ready for reporting and analysis. By following this structured approach, you can build scalable, maintainable, and high-performing data pipelines that empower your teams to make data-driven decisions with confidence. I hope this session was insightful and helps you leverage DBT effectively in your projects. Thanks for watching, and happy modeling!